In this video, we're going to do some solution stoichiometry and chemical analysis. For solution stoichiometry problems, we'll apply the same principles for any reaction stoichiometry problem. The only difference is sometimes it'll be easier to consider the net ionic equation and only consider the species that are actually reacting and actually present in the solution. And we'll be using molarity and volume to help us determine moles of reactants and products. Here's a sample problem for us. Let's calculate the mass of solid sodium chloride that must be added to 1.50 liters of a 0.100 molar silver nitrate solution in order to precipitate all the silver ions in the form of silver chloride. So we need to do some stoichiometry, which means we're going to need a balanced chemical equation. So we're going to add sodium chloride to a silver nitrate solution in order to precipitate silver chloride. This will be our precipitate. And sodium nitrate will be spectator ions. So we have a balanced chemical equation, which means we can do some stoichiometry. Now, we got 1.50 liters of the silver nitrate solution. And let's convert that into moles. When in doubt, mole it out. 0.100 moles of silver nitrate for every liter of solution. So this is just the molarity that we were given in the problem. Written as a conversion factor to cancel liters and get moles. Well, the question ultimately isn't about silver nitrate. The question was about sodium chloride. So 1 mole of sodium chloride is needed for every 1 mole of silver nitrate that we're reacting because of the 1:1:1:1 stoichiometry in this balanced equation. That'll get us moles of sodium chloride. Question was about the mass of sodium chloride, so we're going to need to calculate the molar mass of sodium chloride in order to convert that into grams. So I'm going to grab my calculator and I'm going to take a peek at a periodic table. I'm sure I've got one here somewhere. Sodium 22.99, chlorine 35.45. Together, that's 58.44 grams for every mole of sodium chloride. So now we're actually ready. If we multiply everything on the top, divide by everything on the bottom, the only unit that didn't cancel is the mass of sodium chloride. And so with 3 significant digits, we get 8.77 grams of sodium chloride. That's what's necessary to precipitate out all the silver ions out of the silver nitrate, as shown here. Here's another problem for us. When aqueous solutions of sodium sulfate and lead-2 nitrate are mixed, lead-2 sulfate precipitates. Calculate the mass of lead-2 sulfate formed when 1.25 liters of 0.05 molar lead-2 nitrate and 2 liters of 0.025 molar sodium sulfate are mixed. All right, we got another stoichiometry problem, so we need to do another balanced chemical equation. But for this problem, since I already know what the precipitate is, I'm just going to take a look at the net ionic equation. And so we've got lead-2 from the lead-2 nitrate reacting with sulfate from the sodium sulfate to produce lead-2 sulfate as the precipitate. Now we need to find the mass of precipitate that forms in this reaction. We don't know what our limiting reactant is, so let's see if we can figure that out. 1.25 liters of the lead solution that has a concentration of 0.05 0.00 moles of lead 2 ions per liter of the solution. Lead 2 nitrate only has one lead ion in it, so the concentration of the lead 2 nitrate solution is the concentration of the lead 2 ions in the solution. So if we got 1.25 liters times 0.05 moles per liter, we're going to have 0.0625 moles of lead ions present in this solution before any reaction takes place. All right, we got 2 liters of the other solution, which has the sulfate in it. And this one also, sodium sulfate only has 1 mole of sulfate for every mole of sodium sulfate. So the concentration of sodium sulfate is the concentration of sulfate in the solution. 0.0250 moles of sulfate ions for every liter of solution. And this gives us 0.0500 moles of sulfate ions in the solution. All right, so it's a 1-to-1 stoichiometric ratio of lead 2 and sulfate ions in the equation. But you can see we have less sulfate ions present, so this is definitely our limiting reactant. So all of our stoichiometry calculations should be based on this. If we're going to figure out the mass of lead 2 sulfate that gets produced, we need to use the limiting reactants, moles or volume, but I've already done this calculation once, I don't need to do it again. So we've got 0.0500 moles of sulfate ions that are going to react. We're going to react that with 0.0500 moles of the lead 2 ions to produce lead 2 sulfate. So 1 mole of lead 2 sulfate is produced for every 1 mole of sulfate ions based on the stoichiometry in the balanced equation. So we're going to get, I don't care about how many moles that is, although I could probably guess that it's 0.0500 moles. Let's figure out what the mass is. How many grams of lead 2 sulfate is that? Well, we're going to need the molar mass of lead 2 sulfate. So, looking at my periodic table here, lead is 207.2, sulfur is 32.06. There are 4 oxygens at 16 apiece, so I'm getting 303.26 grams of lead 2 sulfate for every mole of lead 2 sulfate. Multiply that by 0.0500 moles of sulfate. This conversion factor, the ones cancel out, and we get 1.52 grams of lead 2 sulfate is our final answer. That's our mass of precipitate formed. So generally speaking, these are the steps we can use to solve stoichiometry problems that take place in solution. It even works for acid-base neutralization problems, like this one. What volume of 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of 0.35 molar sodium hydroxide? All right, so we've got an acid-base neutralization reaction taking place in solution. Of course, we need a balanced chemical equation. It's a strong acid reacting with a strong base. So you're not going to have hydrogen chloride molecules in solution. You're going to have hydrogen ions and chloride ions. Chloride ions aren't going to react with anything. You're not going to have sodium hydroxide in the solution. You're going to have sodium ions and hydroxide ions, and the sodium ions aren't going to react. But the H plus from hydrochloric acid and the OH minus from sodium hydroxide, those two will react and produce water. So we got a 1-to-1 stoichiometric ratio, as you might have predicted. So to find the volume of the acid solution that we need to neutralize 25.0 milliliters of 0.350 moles of sodium hydroxide, or I guess better yet, just hydroxide ions, because there's 1 mole of hydroxide for every mole of sodium hydroxide. This is the number of moles in 1,000 milliliters of solution. So this will get us to moles of hydroxide. We got 1 mole of H plus for every 1 mole of hydroxide. This will get us the number of moles of H plus. And ultimately the question's about hydrochloric acid, so I'm going to go ahead and convert to HCl molecules, even though I wouldn't necessarily have to do this, because the stoichiometry on this one's pretty easy and the ratios are 1-to-1 ratios. But this gets me how many moles of HCl I need to completely react with all of the hydroxide in this solution to take this reaction to completion. I don't really care what this answer is, because it's going to give me moles of hydrochloric acid. So I actually just need to divide all this, or I'll just divide over here. Nope, I don't want to do that. Sorry, I do care what this is. Let's find out what this is. 25 times 0.35 divided by 1,000 times 1 times 1. So I get 0.00875 with 3 sig figs. That's how many moles of HCl are present. I forgot what the question was. The question was, what volume of this solution will I need? I know the concentration of the solution, so I can put that on the bottom, 0.100 moles of HCl solution for every liter of HCl solution. And this is going to get me 0.0875 liters of HCl solution with this concentration. So this is 87.5 milliliters. This problem has 2 parts, but we'll apply the same problem-solving steps we've been using. In a certain experiment, 28 milliliters of 0.25 molar nitric acid and 53 milliliters of 0.32 molar potassium hydroxide are mixed. Calculate the amount of water formed in the resulting reaction. What is the concentration of H plus ions or hydroxide ions in excess after the reaction goes to completion? All right, so we got another limiting reactant stoichiometry problem. We're reacting nitric acid with potassium hydroxide, which is going to give us water, and potassium nitrate. So the only real way we'll know this is a reaction taking place, because the H plus in solution, these are all colorless solutions, so maybe we would measure temperature change, or if we used an indicator, maybe the indicator would change color and we'd know that a reaction was going on. But we've got the H plus from nitric acid and the OH minus from potassium hydroxide forming water molecules. And the question is, what amount of water molecules are going to form in this reaction? Well, we've got 28.0 milliliters of nitric acid, concentration 0.250 moles per liter, or 1,000 milliliters. So this is, well, you know what? Since we're going to figure out how many moles of the product are present, might as well figure that out now. 1 mole of water for every 1 mole of HNO3. So we got 28 milliliters times 0.25 divided by 1,000. And we got 0.00700 moles of water if this is the limiting reactant. Not sure yet. So we got 53.0 milliliters of potassium hydroxide, which is 0.320 moles of potassium hydroxide per 1,000 milliliters. Again, it's a 1-to-1 ratio, 1 mole of water is produced from every 1 mole of KOH. This is going to be 53 times 0.32 divided by 1,000, 0.01696, so 0.0170 with 3 sig figs. So this is our limiting reactant, nitric acid. So our answer to the first question is 7.00 times 10 to the negative third moles of water, or 0.00700 moles of water. Now we need to figure out what's the concentration of the excess hydroxide in this solution. So potassium hydroxide is going to not be used up. There's going to be excess hydroxide. Well, if this is this number here is the moles of hydroxide ions that are present before any reaction takes place. This is a 1-to-1 ratio here. So we're going to be using 0.00700 moles of the hydroxide. So this is how much was present initially. This is how much gets used up because of the 1-to-1 stoichiometric ratio here. So 0.0170 minus 0.00700, and we got 0.0100 moles of hydroxide left over. But the question wasn't how many moles of hydroxide are left over. The question is, what's the concentration after the reaction goes to completion? Well, this is how many moles of hydroxide are going to be in excess in this solution. And this isn't the concentration because it's not a liter of solution. It's 28 milliliters and 53 milliliters. So 53 milliliters and 28 milliliters, that's 81 milliliters total. So 0.0100 moles of OH minus for every 0.0810 liters of solution. Just added these two volumes together and I converted to liters. So 0.01 divided by 0.0810 is going to give us 0.123 moles per liter of hydroxide, which is the final answer for the second question. The next couple of problems are titration problems, so let's go over some terms related to titration. First of all, titration involves delivery from a burette, a very precisely known volume of a solution, typically with known concentration. That's called the titrant. That's in the burette, and you drop it into a solution that you're trying to analyze. That's called the analyte. Generally speaking, you know the concentration of what's in the burette, but you don't know the concentration of what's in the flask that you're titrating into. But it can work the other way around too, as long as you know one of the solution's concentrations. The equivalence point is the point in the titration where enough titrant has been added so that it's reacted completely. It's a stoichiometric point, reacted completely with the analyte. The end point, on the other hand, is when your indicator changes color. While you want your end point to be near your equivalence point, this isn't always the case. Since you want the reaction to go to completion during an acid-base titration, your titrant should typically be a strong acid or a strong base, depending on whether you're titrating into a base or an acid. A common indicator for acid-base titration is phenolphthalein. It's a colorless and acidic solution, but it turns pink in basic solution. So the end point is very easy to see. Here's a great example of a real-world application of titration and neutralization. So a student wants to carry out an experiment. So they're going to standardize and determine the exact concentration of a sodium hydroxide solution. They may know that it's, around 0.15 molar or something like that, but this process will allow them to precisely determine what the concentration is, with more than just a couple of significant digits. So to do that, the student masses out 1.3009 grams of potassium hydrogen phthalate, abbreviated as KHP.
and the molar mass is shown here as well. Important to note, this has only one acidic hydrogen. The student dissolves the KHP in distilled water and adds phenolphthalein as an indicator, titrating the solution to the endpoint with sodium hydroxide. The difference between the final and initial burette readings for the titrant of sodium hydroxide shows that there's 41.20 milliliters of sodium hydroxide that was used to react with the 1.3009 grams of KHP. Let's calculate the concentration of sodium hydroxide solution.
So this question may seem like a doozy, but it really isn't. Since KHP has one ionizable proton, then it's going to react with sodium hydroxide in a 1-to-1 ratio. And we're going to get sodium potassium phthalate and water molecules. So if we know how many moles of KHP are present, we'll know how many moles of sodium hydroxide reacted with it. And then we'll just divide by the volume of sodium hydroxide that was used to get the molarity. So we got 1.3009 grams of KHP. In the problem we were given, we know that the molar mass of KHP is 204.22 grams per mole. So put grams on the bottom so it cancels. I'll get moles of KHP. Of course, 1 mole of sodium hydroxide reacts with 1 mole of KHP. And this will give us, well, you know what, I don't really care what this gives us, because this is going to give us moles of sodium hydroxide. I'm just going to divide all of this by the volume of sodium hydroxide that we used, was 0.04120 liters of solution, because it was 41.20 milliliters was the difference between the initial burette reading of sodium hydroxide and the final burette reading. So whatever this is the number of moles of sodium hydroxide divided by the volume of the solution, and we got the concentration, which is what we're looking for. So 1.3009 divided by 204.22 times 1 divided by 1, and then I'll divide by 0.04120, and we got 4 significant digits here. So we got 0.1546 molar sodium hydroxide, which is now standardized. So we got 4 significant digits on the concentration for the sodium hydroxide, which will be really useful for using this standard sodium hydroxide now for another titration.
Like maybe this one. An environmental chemist analyzes the effluent, that's the released waste material, from an industrial process known to produce the compounds carbon tetrachloride and benzoic acid. Benzoic acid is a weak acid that has 1 acidic hydrogen atom per molecule. A sample of this effluent weighing 0.3518 grams was shaken with water, and the resulting aqueous solution required 10.59 milliliters of the previously standardized 0.1546 molar sodium hydroxide for neutralization. Let's calculate the mass percent of benzoic acid in the original sample. I'm actually going to leave you to do this one on your own, so pause the video now, and you can check your work with mine in about 10 seconds. How'd it go? I got 56.82% benzoic acid in the sample. Check your work with mine, and be sure to follow up if you have any questions. Later!